In number 18 from homework 3, we're given this hint to use polynomial division in order to evaluate this indefinite integral, and there's actually a shortcut that makes the process a lot quicker, but we'll go through it both ways. So for polynomial division, you can either use synthetic division if you're familiar with that, or you can use the standard sort of long division notation. So we're dividing x squared by x squared plus 1. We know that x squared plus 1 goes into x squared one time. We subtract x squared plus 1 from x squared. That leaves us with negative 1, and x squared doesn't go into negative 1. So we have a remainder of minus 1. And what that means is that our integral x squared over x squared plus 1 dx can actually be rewritten as the integral of 1 minus 1 over x squared plus 1. Okay, now it's a good idea to sort of check your work. If you combine these two fractions by finding a common denominator, you should find that you get exactly what we started with, x squared over x squared plus 1. Now at this point we're ready to take the antiderivative, because we know that antiderivative of 1 is x. We should recognize 1 over x squared plus 1 as the antiderivative of arctan, or tan inverse. So we get x minus arctan of x, and then plus our arbitrary constant. A shortcut that allows us to bypass using polynomial division for this particular problem. This isn't going to work in every case, but if you notice that by adding 1 and then subtracting 1 in the numerator, where I'm not actually changing anything, because really all I'm doing is adding 0, I'm able to split the fraction up into two fractions. So I can group together the x squared plus 1 up top, getting x squared plus 1 over x squared plus 1, and then break off the minus 1, which gives me minus 1 over x squared plus 1. And now if you notice, the first term is the same in the numerator and denominator, so we can simplify that to 1. And then we have negative 1 over x squared plus 1, which is of course where we ended up last time after polynomial division. So from here on out it's the same, but this is kind of a nice trick that you can use when you have rational functions that look kind of like this.